So today we will be discussing the Langevin's classical theory of diamagnetism. Consider an electron revolving in a circular orbit around a nucleus, and the force experienced by the electron will be the centripetal force as well as the electrostatic force. Centripetal force, which is given by mv square by r, is balanced by the electrostatic force given as ze square upon 4 pi epsilon 0 r square, where z is the number of protons inside the nucleus, which causes the electrostatic force, and r is the distance from the nucleus to the electron. And v can be further written in the form of angular frequency as r omega, where omega naught is the frequency of the electron, angular frequency of the electron in the circular orbit. And again we can write this as z e square upon 4 pi epsilon 0 r square. Now this can be written as m r omega naught square equals z e square upon 4 pi epsilon 0 r square. Now angular frequency can be expressed as root over z e square upon 4 pi m epsilon 0 r cube. So this is the expression for angular frequency of the electron. Now consider the case when we apply an external magnetic field on this atom. Then an additional term due to the Lorentz force comes into picture. The electron in the circular orbit is also affected by the magnetic field and the Lorentz force resulting from it. The Lorentz force is given by, so on the application of external magnetic field, on the application of external magnetic field, the Lorentz force is given by F equals minus E times V cross B, where V is the velocity of the electron and B is the external magnetic field, and E is the electronic charge. Negative sign is due to the negative charge of the electron. Now we know that again V can be written as omega r cross B. Now assuming that the B magnetic field is perpendicular to the plane of the orbit of electron, again assuming that the applied magnetic field is perpendicular to the plane of the circular orbit of the electron, then this term can be written as minus E omega RB. So this will be the Lorentz force term. And now one thing to note here is that this angular frequency before the application of magnetic field is not the same once we apply the magnetic field. So the new angular frequency is omega, while the angular frequency before the application of magnetic field was omega naught. Now the electron in the circular orbit is moving with a different angular frequency, and this is not the equation which governs the, or this is not the equation which balances the electron in the circular orbit. So the new equation will be of the form m omega square r equals z e square upon 4 pi epsilon naught r square minus E omega RB. So this is the new equation which will be balancing the electron, which will be acting upon the which will describe the forces which are acting on the electron. So this is the new centripetal force which is acting on the electron, and this is the electrostatic force term, and this is the Lorentz force term. Now from this we have to obtain the angular frequency omega. For that we first divide the whole equation by mr, divide with mr term. So we will be getting omega square equals ze square by 4 pi m r epsilon naught r square minus e omega rb upon mr. Here I'll just show that mr upon mr. So this will be given by omega square equals r square, and r becomes r cube, so ze square upon 4 pi m epsilon 0 r cube minus r cancels and e omega b upon m. Again, this can be written in the form as omega square plus eb upon m times omega minus ze square upon 4 pi m epsilon 0 r cube equals 0. So this is the form of a quadratic equation of omega. Now we can obtain the value of omega using the standard formula minus b plus minus root under b square minus 4ac upon 2a. Omega equals minus eb by m plus minus root over eb by m whole square minus 4 to minus ze square upon 4 pi m epsilon 0 r cube upon 2. Again, one thing that I forgot to substitute here was this term ze square upon 4 pi m epsilon 0 r cube was nothing but our original angular frequency before the application of the magnetic field. So we just need to substitute that here. So this term becomes omega square plus eb upon m omega minus omega naught square equals omega. Since omega naught was root over this term, omega naught square is this value. Now again substituting for omega naught here, omega naught square here, so this will be minus eb upon m plus minus root over eb upon m square plus minus and minus becomes plus 4 omega naught square upon 2. So taking 4 common from these equations, so we just have to multiply and divide by 4 in this term. So this becomes minus eb by m plus minus under root, multiplying and dividing this term with 4 means inside the bracket it becomes 2 since there is a square outside. So this becomes 2 4 EB upon 2m whole square plus 4 omega naught square upon 2, and this gives, taking the 4 common and outside the root it becomes 2. So again minus EB by m plus minus 2 under root EB upon 2m whole square plus omega naught square upon 2. So just dividing this term, this 2, both the terms, so this becomes minus EB upon 2m plus minus under root EB upon m 2m whole square plus omega naught square. And in the case when this angular frequency omega naught, this omega naught is much greater than, if omega naught is much greater than EB upon 2m, this term, then EB upon 2m whole square will be negligible compared to omega naught square. So we can neglect this term, and finally omega becomes minus EB upon 2m plus minus root under omega naught square. So this will be plus minus omega naught minus EB upon 2m. So this will be the new frequency, new angular frequency of the electron moving in the circular orbit in the presence of an external magnetic field. Now it's clear from this equation that there can be two values of omega. It can be either plus omega naught minus EB by 2m or minus omega naught minus EB by 2m. Omega is less than omega naught. Here omega is less than omega naught, and here due to the two negative signs omega is greater than omega naught. That is, in this case, in the first case, the electron after the magnetic field is applied, the electron is slowed down or its angular frequency reduces. In the second case, after the application of magnetic field, the electron gets speeded up or its angular frequency increases. Now consider an electron revolving around a nucleus, and we know the direction of the angular momentum is given in this direction, while the magnetic moment is opposite to that of angular momentum. And the magnetic field due to this revolving electron given in this direction. Which is given by right hand rule, which says that the magnetic field due to the revolving electron is in this direction. That means there is a north pole here and a south pole here, because magnetic field is from north pole to south pole. And so it is clear that the magnetic moment is always in the direction of the north pole. Magnetic moment is always in the direction of the north pole. So now, this is just an imaginary north pole and south pole. This is assumed because of the direction of the magnetic field. So this, as you already know, this rotating electron or revolving electron acts like a magnet, acts like a bar magnet. So coming back to the case of our electron revolving around the nucleus, and when we apply an external magnetic field, we have seen that after the application of magnetic field, its angular frequency either increases or decreases. That is, it either speeds up or slowed down. In this case, where the two negative signs, it speeds up. And in this case, it slows down. Its angular frequency decreases. And now in this case, this is the same electron, suppose, and this is the magnetic field due to the revolution of the electron. The electron revolving around the nucleus acts as a bar magnet, and it creates a magnetic field in this way. Now we apply a magnetic field externally, and if the external magnetic field is in this direction, if the external magnetic field is in this direction, means the north pole of the external magnet is here and the south pole is here. So this is the external magnetic field. So this means the external magnetic field is applied in this direction, that is the direction opposite to the magnetic moment of the electron. So when the external magnetic field is opposite to the direction of magnetic moment of electron, the north pole of the external magnetic field source and the north pole of the magnetic field created due to the revolution of the electron, both are in the same direction. That is, the poles are coming together, or there is a chance for repulsion, which creates a repulsive energy, and this speeds up the electron. This speeds up the electron, causing the angular frequency to increase. And now, if the external magnetic field is in the opposite direction, if the external magnetic field is in the opposite direction, if the external magnetic field is in this direction, that is, its north pole is here and its south pole is here, or in other words, the external magnetic field is in the same direction as the magnetic moment given by mu L. The external magnetic field is in the same direction as mu L, which means the south pole of the external magnetic field and the north pole of the magnetic field due to the revolving electron orients in the same direction. That means there is an attractive force or attractive energy. This causes the electron to slow down, or its angular frequency decreases. So the case 1 is if magnetic field or magnetic moment, if magnetic moment is parallel to the direction of the external magnetic field. The electron so what happens if the magnetic moment is parallel to the direction of the external magnetic field? If the magnetic moment is parallel to the direction of the external magnetic field, that is this case. In this case, what happens is the south pole and north pole comes together, which means there is an attractive energy. Then the electron slows down. Or its angular frequency decreases. Omega is less than omega naught. Angular frequency is decreased. Now the second case, if magnetic moment is anti-parallel to the direction of the electric field of the external magnetic field, the electron speeds up. Here, if the magnetic moment is anti-parallel to the direction of the external magnetic field. So if the magnetic moment is in this direction, downward direction, and external magnetic field is in the upward direction, that is they are anti-parallel, then the north pole and north pole comes together. So there is a repulsive energy. Repulsive energy is causing the electron to go faster, or it speeds up. That is, angular frequency increases. So again, remember this magnetic field which I have drawn with blue ink. This is due to the magnetic field of the revolving electron. Magnetic field created by the revolving electron. While this field lines in red ink is due to the external magnetic field. Is the magnetic field we apply from some external source. So we've seen that the application of magnetic field, the application of magnetic field or the application of external magnetic field creates an additional angular frequency, causes an additional change in angular frequency, either decreases the angular frequency by a particular amount or increases the angular frequency by a particular amount. This increase or decrease in angular frequency, or this magnitude of increase or decrease of angular frequency, is given by delta omega equals EB upon 2m. This is the same term given here, EB upon 2m. Corresponding frequency can be obtained by the equation delta omega equals 2 pi delta nu, where delta nu equals delta omega upon 2 pi equals delta omega is EB upon 2m upon 2 pi, which becomes EB upon 4 pi m. So this is the additional frequency which by which the electron is slowed down or speeded up. And due to this additional frequency, it results in an additional current. The additional current, which is given by current I is given by charge times the number of revolutions per unit time. Here charge is minus E times revolutions per unit time is same as the frequency, EB upon 4 pi m. Due to this additional current, there is an additional change in magnetic moment. We know that magnetic moment of electron is given by I cross or I into A, where I is the current and A is the area of the circular loop or the area of the circular orbit, and I is E square B upon 4 pi m. And now substituting the value of I here, minus E square B upon 4 pi m times area. Area is the area of the circular orbit, which is pi r square. This can be written as minus E square B r square upon 4m.